Now that you've learned how to find information about individual elements, it's time to look at the whole periodic table of the elements in order to see larger patterns that can only be seen if we look at all of the elements on the periodic table as a whole. Now, the first of these patterns you actually already know, and you can see this by looking at the atomic numbers of each individual element. Remember that the atomic number is the number found in the top left corner of each element's box, which corresponds to the number of protons that that element has. Now, if we look at atomic number across the periodic table, we can see that as we start on the left-hand side and go towards the right-hand side, the same way that we read English, we can see that the atomic number increases as we move from left to right on the periodic table. And we can see this: hydrogen is 1, helium is 2, go down to the second level, and lithium is 3, beryllium is 4, boron is 5, and so on. Now, there's two pieces of terminology we need to get out of the way. Instead of referring to the horizontal and the vertical strictly as right to left and up and down, we're going to start using two specific names. So if you were to read the periodic table horizontally, we would call each horizontal row a period, hence the term periodic table. Now, as we go down the periodic table, we see that each of the periods is given the number. Hydrogen and helium's period is number 1. Lithium's up to neon's period is 2. Sodium's over to argon's is period 3, and so on. Now, the reason why elements are organized like this is that each period represents an electron shell. So remember that electron shells are the circular orbit-like structures that where the electrons travel outside of the nucleus, and every time we go down a period on the periodic table, we are adding a new electron shell. So, for example, hydrogen and helium only have one electron shell, whereas the elements from lithium all the way to neon have the first electron shell that hydrogen and helium have, plus a second shell on top of that, and so on. Now, if we look vertically instead of horizontally, so if we look at columns on the periodic table, each of these columns is what we call a group. So we can see that groups are also labeled. So hydrogen, lithium, sodium, potassium is group 1, or it's known as the Roman numeral notation down here, which is 1A. Beryllium downward is group 2, also called Roman numeral 2A. Then we have the middle of the periodic table, which we get to if we skip to boron. Boron's group is often called group 13, also called Roman numeral 3A, and so on. Now, the elements are grouped in groups. That sounds a little bit silly. Each element in the same group exists in the same group because they have the same number of valence electrons. So remember that electrons are the subatomic particles that exist outside of the nucleus, and the valence shell of electrons is the outermost shell. So if we look at the outermost valence shell of hydrogen, lithium, sodium, potassium, and so on, all of them will have the same number of electrons in the outermost shell, and the same is true for beryllium, magnesium, calcium, strontium, etc. So this is why the periodic table is structured the way that it does. We can look at simply which period and which group an element is in order to determine how many electron shells that element has and how many electrons exist in the valence shell. Now, you'll notice that this version of the periodic table is colored. You will notice that if we looked on the left-hand side of the periodic table, we can see that all of these elements are labeled in green. That's because all of these elements are metals. So the periodic table is grouped into generally two halves, although the halves are not the same size. Basically, on this dividing line here to the left are the metals, and everything right of this line would be the elements that are not metals, known by the ever so scientific name of nonmetals. Now, there are a very large number of metals, and because of that, we tend to group the metals based on their common behavior into what we call several element families based on common characteristics that they have. So let's go through a few of these. The first of which are what we call the alkali metals, and the alkali metals are very exciting to study because they are all very, very reactive metals. They are all very, very unstable. This alkali metal is potassium, which is actually shown exploding in a bright purple flame as it touches water. And the reason why they're so reactive is that these metals only have one electron in its valence shell, and we'll talk about why that is significant in the next video. If we go over from the alkali metals to group I believe that's group 2 or group 2A. These are the closely related alkaline earth metals. Don't have enough space to write metals in. Let's just squeeze it in there. And these are also very reactive. We can see in this picture that this metal is being burned and giving off a very bright light. This is magnesium here. So alkaline earth metals are also very reactive, but are slightly less reactive than alkali metals. You need to set magnesium on fire before it does this, unlike the alkali metals that explode when they touch water. And alkali earth metals have 2 electrons in their outermost shell instead of 1, and again we'll see the significance of this. In the middle of the periodic table, so from groups 3 to 12 or 3b all the way to, I believe that's 11b over here, are what we call the transition metals. And to transition means to pass from one side to the other or one form to another. So we call these the transition metals because when you go from one side of the periodic table, from the metal side to the non-metal side, you transition through these metals here, hence the name. So transition metals are interesting because if we zoom in and look at the charges of these metals here, you can see that many of them have more than one charge, and this is not a feature you find on either the far right or the far left of the periodic table, and we use the term multivalent, which simply means more than one charge. And of course we find these because we transition from one side to the other. We find these in the middle of the periodic table. Now, going up here, before we get to the nonmetals, we're going to pass a small family of elements that aren't quite metals and aren't quite nonmetals either, for which we are going to call them metalloids, which means metal-like, but not exactly metals. So metalloids, because they exist between the metals and the nonmetals, have some physical and chemical properties that both metals and nonmetals have. Unfortunately, we won't be studying most of these in Science 9. Now, getting over to the nonmetals here, if we take a look at Group 17 or Group 7A, this is another exciting family of elements that we call the halogens that are all very, very reactive nonmetals. So in the same way that the alkali metals are very reactive metals, the halogens are very reactive nonmetals. So this gas inside of this volumetric flask is chlorine gas, which is very, very poisonous. If you were to inhale this, it would form acid inside of your lungs and melt you from the inside out because of how reactive it is. And halogens have 7 valence electrons rather than 1, and again, in the next video, we will see why this is significant. If we get all the way over to the far right-hand side of the periodic table, we get to a family of gases that we call noble gases. And noble gases are special because unlike the halogens that are right next to them, which are all very, very deadly and very, very unsafe, the noble gases are all basically completely unreactive. And the reason why they are completely unreactive is that they have 8 valence electrons. Now, in the next video, we'll look at the significance of having 8 electrons in its outer shell, but the short of this is that noble gases cannot gain or lose electrons because their outer shell is full. And because they can't lose electrons to other elements or take electrons from other elements, they exist perfectly stably and are therefore unreactive. In the next video, we're going to explore the concept of valence shells and actually learn how to construct diagrams of different elements using the information that you can find on the periodic table.